Visible to you guys?
Yes, ma'am.
Okay. So, good evening, everyone. I'm Riya Verma, a PhD research scholar from the Department of Civil Engineering, IIT Roorkee. And today we'll be having your weekly tutorial session for the assignments for week 9, the previous year questions, and we'll also be taking the topics that were discussed during the week 9, that is your pollution control devices. I've taken a few devices from your lecture, and I've attached those presentation slides in this PDF only. So we'll have a small discussion on those devices also, so that this will be a kind of a revision class for that as well. So first question is, which of the following devices is not used to control gases from the stationary sources? So, among all these four devices, which one is not to control the gases? Like, not. Just clearly see this word. Not to control the gases from stationary sources. So, any idea about that? Your options are like first is your spray tower, next is your packed towers, then we have Venturi scrubbers, and then we have fabric filters.
Fabric filters.
Yes, and any idea about the reason that why it will be fabric filters?
Fabric filters are used to filter particulate matter.
Yeah, true. Okay, so just we'll have a brief discussion about the devices for different type of pollutant sources, like what kind of device are used for which type of source. So basically, see, when talking about the maintenance of the air quality, like when we have to maintain a certain level of air quality, then the best way is to reduce the emission of the pollutants. And if we are not capable of doing that, like we are not able to control at source, then another way is to like to some way alter their composition, or somehow to remove them once they are released from their sources and are being um are they are like transferred to longer distances, and they are present in the atmosphere. Then the other way is to just trap them from there, and to remove them. So the devices for your control of particulates from stationary sources. So for the stationary sources, we have your settling chambers, we have inertial separators, we have cyclones, then we have scrubbers like wet scrubbers, and then we have ESPs, electrostatic precipitators, and then fabric filters. So these are for the control of particulates from the stationary sources. When the source is stationary, for example, any industrial setting, then we can use for these. Next, that is for particulates. Now coming towards the control of gases from stationary sources. Excuse me, just a second. Yeah, sorry for that. So the devices that are being used to control the gases from the stationary sources, first is the spray tower, then we have plate towers, then we have packed towers, venturi scrubbers, then some of the adsorbents are also used to control the gases. And also we have combustion or incineration equipments that are for that way we can combust those gases, and then remove them, or they can form precipitates and can be removed by that process. Now coming towards the mobile sources. So the methods for control of emission from mobile sources, first we have exhaust gas recirculation, EGR system. Then we have air injection system. Then we have catalytic converters. So these are important. Catalytic converters, basically these are used to reduce the tailpipe emissions from the vehicles. And next up, we have positive crankcase ventilation valve (PCVV) and evaporative control systems. So also there are some devices that are used to control the pollutants from the area sources. For example, agricultural emissions when we have those. So for the control of dust and particulate matter, what we can do is we can maintain the soil surface cover. If the soil surface cover is we have vegetation over the soil, then like particulates are not uh, blown by the wind and they don't get suspended in the air. Then also we can create some wind barriers, and either this can be a type of vegetative barrier or artificial barriers. This kind of setting you can easily visualize around yourself. Like at some places, what people usually do is they put long plants or trees in the boundary wall of their fields. So this creates a kind of wind barrier and helps in reducing the soil erosion from their fields. So this is also one type of method that in that way we can control the particulates. Next up, we have a crop residue burning. This is a huge problem. Basically, what happens is during the harvesting season, when these crops gets harvested and we get grains extracted from them, we tend to burn out the residue, whatever is left in the fields, and that creates a lot of pollution in the air. So what alternatives that we can go for is, first is composting the residue. Whatever the residue is left in the field, we can go for composting, and that way we can get a huge amount of manures, and this compost can be further used in the fields as manure. Then we have production of biochar. We can also produce biochar from them, and then it can be used as an adsorbent. Then we have some mechanical devices, for example, the happy seeder, the straw management unit that cuts, lifts, and throws the standing stubble and loose straw into the sown area behind the seed drill, which sows into the bare soil. So this kind of mechanisms are there. Now, when we want to control the pollution uh, from the area source. For example, a forest fire is there. So how do we control the pollution from there? Like how do we control the forest fires? So first is there we should have a firefighting reservoir in such areas, like for example near some forest. If place has some amount of forest cover, then we should have some firefighting reservoir so that water can be easily available in case of forest fires. Next is the spraying of fire retardant. This spray can be done on the trees so that there is a the chances of the forest fires are minimized. Then we also have forest fire monitoring systems. In that we can do aerial surveillance, and also at some places we can have fire watchdogs as well. So these are the control mechanisms for different types of sources of air pollution. So, coming towards the next question. Also, please feel free to ask your doubts as and when they arise. Whenever I'm discussing something, if you feel that you are not understanding something or you are having any doubt on any topic, you just stop me in between and then ask your doubts. Okay, so next up we have select the suitable device used to control the industrial dust emissions. Hmm. So we have first option as settling chamber. Next up we have catalytic converter, then PCVV, and then next is all of the above. Anyone?
All of the above.
Industrial dust emissions. This can't be all of the above because this PCVV was used for your mobile sources, right? This one. This is control of emissions from mobile sources. And here we are asking about industrial dust emissions. So this will come under the stationary sources, right?
मैम कैटालिटिक कन्वर्टर से क्या डस्ट रिमूव होता है?
बेसिकली कैटालिटिक कन्वर्टर जो है वो हमारे टेल पाइप एमिशंस के लिए होता है, तो उससे भी पार्टिकुलेट्स लाइक स्मॉलर फाइनर पार्टिकल्स जो होते हैं, फाइनर पार्टिकुलेट्स, दे
हाँ,
दे गेट रिमूव्ड.
I think it's work on only the gases like carbon dioxide, NOx, like this. That's why I'm asking.
Sorry, no, it can remove the gases as well as pollutants that are there from the exhaust. Basically, the vehicle exhaust, whatever that is coming from there only, na, it it removes that.
Okay, ma'am.
Okay, so coming towards this catalytic converter, basically what it does is, you were right that it removes your like it converts your harmful gases like carbon monoxide and hydrocarbons, and uh, into some other forms that are like less harmful. But there are few attachments that can be used with that in the tailpipe. Like we have this zero like zero C, 0.25 something. There's one device that has been patented few months back. So that can be used in the tailpipe. What it does, it charges the like finer particles from that are being emitted from the tailpipe, and then they act as like um, they get charged up and they attract the larger particles. So there is some amount of coagulation happening there. So that is how this particulate matter gets removed. So a catalytic converter alone can't remove the particulates. It's basically designed for gaseous emissions. Sorry, I was there now. So this industrial dust emissions, we have this settling chamber that can be used for that. So for control of particulates from stationary sources, we can remove these airborne particles by a variety of physical methods. So first one is your like coagulation mechanism. What it does is, the once collected, the particulates tend to adhere to each other, and like the finer particles tend to form a bigger flocks of particles, and thus they can be removed very easily. So the devices that can be used to remove such particulate matters, these are like your settling chambers and cyclonic collectors that can be used to control the industrial dust emissions, as well as the pre-cleaners for other kinds of other collection devices. Now we also have wet scrubbers. So basically these are used to control the more flammable or the explosive dust from those industries which process certain type of chemicals or other type of hazardous waste they generate. So we can use wet scrubbers in those areas because they can handle hot air streams, which generally these your settling chambers and cyclonic separators can't do. And these ESPs and fabric filters are used to collect the dust, oftenly at power plants. Now, the next question. From the cost and removal efficiency perspective, which of the following pollutant control devices is preferred for effective removal of the particulates over 40 micrometer in size? So, first up, we have inertial separators, cyclonic separators, then settling chambers, and then ESPs, electrostatic precipitators. Okay, so this will be your settling chamber. Basically, it is designed to collect the particles which are heavier in size, which generally get the particles that are generally coagulated and have formed bigger flocks. They can be removed very easily in the settling chambers. So basically, it is a very simple type of equipment that is used for the collection of solid particulates. Here we have a gas inlet, and the gas enters from this inlet chamber, and then what we do is we generate the gas here enters at a certain flow rate. Then we increase the area of the chamber. So what happens is as we increase the area of the chamber, basically see the flow rate is what Q is equals to area multiplied by volume of gas. So the volume of the gas is same. Whatever is entering, it's the same amount of gas that is entering from this chamber. So since, sorry, this not volume, this is velocity. Very sorry, very sorry. This is Q is area into velocity. So what happens is a certain amount of gas is entering from this inlet chamber. When we increase the area of this chamber now, what happens is this flow rate is the same. So while increasing the area, this velocity of the gas tends to decrease. And when it decreases, what happens is the particulates that are present in that gas, they tend to settle down in these collection hoppers, dust collection hoppers. And after that, we have this outlet, and this is used to the clean gas comes out of this chamber, outlet chamber. So this is the principle of your settling chamber. This is the same, basically, this is the mechanism or the principle they've explained. But the general principle that I've described, it's quite the same. This Q is, that is the flow rate is constant. And while increasing the area of the chamber, the velocity gets reduced. And due to this reduction in the velocity, uh, let's have a quick look at this principle that they have tried to explain. That they've assumed that the solids that move along the chamber with the velocity of the gas, and the settling velocity is your Stokes velocity. So the particle entering at the chamber at the top will be collected by the chamber if its settling time is the same or less than the time the gas takes to pass through the chamber. So they have derived this diameter of the particle, that this diameter of the particle, this is the minimum size of the particle that can be removed from a settling chamber. How did we get into this equation? This is by Stokes law. We have this settling velocity is small g multiplied by density of the particle minus density of the air into d square by 18 mu. Here d is the diameter of the particle, and mu is your viscosity of the gas. So by rearranging this equation and putting the value of Vs as HV by L, we get this D as, this should be 1 by 2. It's not 1 T2. This should be 1 by 2. This is under root 18 VH by L 0 P minus rho. Now, what are the important aspects of these settling chambers? That is that the gas velocity must be sufficiently low, that is less than about 3 meters per second, to prevent the re-entrainment of the settled particles. What happens is, if the velocity is not very low, after some time, the settled particles, if the velocity is higher, they tend to re-entrain in that airstream and can come out of this gas chamber. So, on this outlet chamber. So the velocity must be sufficiently low. To minimize the turbulence and ensure the uniform velocity, we can use curtains or rods and wire mesh screens inside these chambers. And the pressure drop generally is very small in this chamber, and it's mainly the losses at the entrance and the exit. So how can we improve the efficiency of these settling chambers? First of all, is we can reduce the height of like uh, the height to be traveled by the particle. If we can reduce somehow that height, this height, then what will happen is the minimum size of particle is gets will get reduced. So the more efficiency would have been achieved. And also we can place horizontal trays or shelves in the settling chamber about 1 to 3 centimeter height intervals. And after that, if we install that, the minimum size of particle that can be removed after that is approximately 10 microns. Now, what are the applications of these settling chambers? They can be used to remove the particulates which are more than 40 micrometers in diameter. And however, the finer particulates, as explained before, they can coagulate or agglomerate within each other and form bigger particles, and then we can collect them in the settling chambers. And these are generally used to remove the large solid particles, for example, your draft furnaces or kilns, and also in process industries like food and metallurgical industries. To control the dust, we can use these settling chambers. Generally, these are used as pre-cleaners to increase the efficiency of the like on the downstream side to increase the efficiency of the collectors. What are the advantages of these settling chambers? First one, we have these. Their initial cost is very low. Their construction is relatively simple, and also their maintenance is quite easy and low. There's not much pressure drop, so we don't have to increase the pressure at the outlet chamber. And also the solid particulates, their disposal is dry. There's not they don't get processed in the settling chamber, and there's continuous disposal of these particulates. And it can be constructed out of almost any material that is durable and can resist that much of pressure. And temperature and pressure limitations imposed only by material of construction used. What are the disadvantage of these settling chambers? Basically, they generally require a larger space, and their efficiency is relatively very low. Like particularly for the particulates of less than 50 microns or 40 microns, their efficiency is very much higher. The case in multiple tray settling chamber may warp during the high temperature operations. They can get bent or warped if the temperature is high. Now, next up we have what is the principal collection mechanism that is used in Venturi scrubbers. First is Brownian motion. Next is electrostatic attraction. Then we have inertial impaction, and then we have coagulation. So, what is the principal collection mechanism that is used in Venturi scrubbers? Let's have a look at these wet scrubbers, and then we'll come back to this question. So basically, these wet scrubbers are a set of devices, and these can be used to control both particles as well as gases, because basically these are these can be designed to generate a high inertial forces or electrostatic forces on particles, and they can drive them into droplets or the sheets of liquid. The principal mechanism, basically, the principal mechanism can be either the Brownian motion of the particles, or they can just get impacted by these droplets of water and can have inertial impaction. Then we have your direct interception, then electroscavenging, like the droplet is positively charged and the particles can be negatively charged, so there can be electroscavenging. And then we have phoresis as well. So, first is your Brownian diffusion. So the movement of the particle due to collisions with the air molecules. So this results into a random walk of the particles into the droplet surface. Then we have direct interception. So the particles that follow a streamlined path, they approach the droplet within a distance equivalent to the particle radius, and they can be removed by these water droplets. Then we have inertial impaction, particles that have sufficient inertia and they do not follow their original streamline around the droplet, but instead travel close enough to the surface to result in a collision. And after their collision, they can get washed away by these liquid droplets. Then we have electroscavenging, that opposite electrical charges are present in the droplet and the particle resulting in an attraction between them, and that is how they get removed. Then also we have phoretic forces, like in this way the water droplet can may get evaporate and can grow in size. And we have two type of phoretic forces, that is thermo or the diffusio.
Good
In
evening,
therm
ma'am.
Yes.
Ma'am, I need an important question, ma'am. Could you make this
Yes.
possible?
Yeah, sure.
Ma'am, because of the vast syllabus, I can't able to manage, ma'am. So I need an important questions, ma'am.
Okay. Important questions, like for your NTEM,
Ma'am,
like the exam that you'll be having for that, for all
yes,
three
ma'am.
lectures.
Yes, ma'am.
Okay.
How will be they asked, ma'am? Because some of the points are also highlighted, ma'am. From there will be asked, or where they will be more asked, how many questions they will be asked from the assignment. So much of the doubts are in my mind, ma'am. So could you
Okay.
help me?
I guess as far as I know, you'll be having, I guess, 50 questions in your NTEM. I'm not sure. It's
Assignments, ma'am.
Yeah, and we'll be having like multiple choice questions.
Yes, ma'am.
So, or they will be more sort of your conceptual questions, not too difficult. But
Mhm.
yeah, and also everything will be from your lectures only. Whatever the content they have given in your like slides of the lectures, the questions will be
But
asked from there only. Yeah.
it's so vast, ma'am. In according to me, it's so vast, so I could able to manage, ma'am.
See, there are few topics that are more important as compared to others. For example, like initially your lapse rate, inversion conditions, types of plume behavior, those are stability conditions. So those are some of the important topics. Then after that, in the indoor air pollution, like the causes and effects, like which effect is caused by which type of indoor air pollutant, or what will be the source of a particular air pollutant. So these basic concepts, the
Okay,
questions from there only, and also these your pollution control devices. I feel this is also an important topic, since you'll be having multiple choice questions. So I guess they will not be asking you very detailed numericals, but
okay, ma'am.
I hope they won't ask you very long, like very long numerical. But yeah, the concepts will be asked from these topics, these pollution control devices. Like they may ask you the formula, or they may ask you to like explain a certain, not explain, to use a certain formula and find out certain values. So that kind of questions may be asked there. But basically, some conceptual questions will be there from these pollution control devices. And also, like from the case studies, I feel like there won't be that much questions from the case studies, because those
Okay.
are for your information point of view only. But I'm not saying that there won't be any question, but because might be possible that they give you one or two questions from the case studies as well. So, but these are the important topics that need to be there. Also, uh, I guess we have in the last we have some lab experiments as well. So,
Okay, ma'am. Ma'am, then how
yeah.
many questions they will be asked from the assignments, ma'am?
See,
Of your
it's
guessings, ma'am. Of your
not
guessings, how many questions?
like a certain number of it's not that the same question is getting asked from the assignment. No question will be repeated, I guess, because until now it's not like that ki any question has been repeated from the assignments. But yeah, you can always track the pattern of questions that they are giving, because the person who is making your assignments and the person who will be making your question papers, both are the same. So the pattern of questions, like you can always analyze the what kind of questions are being asked in the assignments. The pattern in the end term will be like that only, not so difficult
Okay,
and not that much easy, but yeah, a bit more conceptualized, I guess.
okay, ma'am.
Also, I guess you'll be having two or three sets of question papers among yourselves. So it depends which set of question paper you are having, because every set will be having different questions, I guess. And rest all, what I can do from my side is I may discuss this with the TAs of this course who are preparing your question papers, and I can have a certain idea about the like what kind of questions will be there. Not exactly the same questions. I can't tell you is like what questions will be there in the exam only. But yeah, I can have a certain idea, or I can ask them like what are the important topics that needed to be like studied for this exam. So in my next class, I'll discuss this with you guys. Is that
Okay,
fine?
ma'am. Thank you. Thank you, ma'am.
Okay. So types of as well as far as types of wet scrubbers are considered, we have spray towers, we have venturi scrubbers, we have cyclone scrubbers, and then we have packed scrubbers and mechanical scrubbers. So first up we have, excuse me, for your spray towers, basically it is a very simple type of wet scrubber. Either it is a round or a rectangular chamber. So what happens is your clean, sorry. What am I doing today? Yeah. So there's a inlet at the bottom of this chamber. From here, the dirty gas gets entered into this chamber. And what happens is this gas travels all the way upwards. And we have installed your water sprays, these pipes that you can see. These all are water sprays that are placed inside this chamber. So the gas is passed this counter current to this water stream. So as soon as this gas tends to move upwards, this flows counter current, the all the particles that are present in this gas stream, they get washed away. Like sorry. So these generally what happens is this water sprays tend to wash away those particles, and these are get collected in this bottom part only, along with that water stream. And generally, these spray towers are effective for particles greater than about 5 micrometers in diameter, that are larger size of particles. And this is your equation for collecting the for the collection efficiency um, of the wet spray towers of a particular size of particle for a particular size of particle. There are certain terms like this VT is your droplets terminal settling velocity. Then we have efficiency due to impaction, that is your eta 1, the formula for that. Then there's this N1, that is your impaction number, how to uh, find out this N1. And with this N1, you can have your impaction collection efficiency. This is all about your spray towers. Now we have Venturi scrubbers. So this is in the shape of your Venturi meter, if you have seen in your fluid labs. So this is in that shape only. So a particulate laden stream is directed through a Venturi tube at a throat velocity of about 60 to 100 meters per second. This is your inlet uh, inlet chamber. Then water sprays are introduced just ahead of the Venturi throat. This is your liquid inlet. These are your liquid inlets. So from this point only, the water sprays are introduced. Like for example, if you can see in this diagram only, this is your inlet, and as the gas moves downward, here the water sprays are being introduced, and then we have an elbow shape where the particles get washed off, and also the gas also passes from here. So the water that contains the dirty water that contains yes.
Ma'am, in the last slide you talked about the impaction number. What is impaction number?
See, this is your specific impaction number. Mm, this is a term. How do I describe this? The definition of this, right? Just, just a second. This impaction number, basically, I don't have the exact definition for that. This is basically this term is used to find the impaction collection efficiency, like how much amount of particulates get removed due to this impaction of this jet sprays with the particulates, and this is for your different types of flow conditions and what kind of like particulates like theoretically the particles are assumed to be spherical. So this is your for your potential flow and this is viscous flow.
Thank you, ma'am.
See, I sorry for that because I don't have the exact definition for this impaction number. Just a term that is used for your collection efficiency. I apologize for that because I don't exactly remember the definition for this term and I don't want to give you any wrong information. So I'll get into this topic and maybe I may explain this in the next class, but I don't think that much is needed. But yeah, for your own information, I will definitely tell you. Okay, now we have these Venturi scrubbers. This is your efficiency for your Venturi scrubbers. And now we have cyclone scrubbers. What here the gas is made to move in circular motions, and this is due to the circular motions. What is we have your centrifugal forces acting on the particulates, and they tend to like strike on the walls of this cyclonic chamber and come down from that come down from that chamber, and this is your like return of contaminated liquid to containment. So basically the gas is continuously swirled around the gas, just as the same in what they do in the dry cyclone. And just a minor change is that that in dry cyclones there are no water sprays. In this wet cyclonic scrubbers we use water sprays, and these water sprays tend to remove the particulates from the walls of the cyclone, and move them towards the center line or the bottom of part of this. And the principal collection mechanisms are impingement and inertial separations of these cyclonic scrubbers. Now, these are other form of scrubbers. This is your packed scrubbers. Basically, it contains of a chamber that has layers of different types of packing material. This is the same, like in one way or the other, it's same as your like sand filters that we use for water filtration. The gas inlet is here. This inlet valve. The gas moves inwards from here. Then as it moves towards the upper section, this packing material traps some of the particulates, and then we have water sprays which washes out that particles, and these get settled out in the bottom, and clean gas is coming out from the top. Now, so one on the same. Now, next up, we have mechanical scrubbers. So these uses mechanical energy to accelerate the gas stream to create conditions which are favorable for the particle impaction. In this, we have a fan type of mechanical aided scrubbers, and there is a single spray nozzle which is in the inlet gas duct, which is used to spray the water. And the particular size efficiency, the particle that is generally greater than 1 micrometers. This can be removed from the mechanical scrubbers. The applications of these wet scrubbers. So basically, these are useful in case of hot gases because of it like it serves us two purposes. First one, it can be used to remove the particulates as well as the harmful gases from your airstream, and next it can also cool down the gas stream. So that way, it's very useful. And when the particulate is combustible, so or any other flammable gas is present in the airstream, so we can't get for any other treatment process. And but this wet scrubbing method, this is useful in such cases. And also where a wastewater treatment system is available on site with adequate reserve capacity to handle the liquid effluent, we can go for this wet scrubbing process, because in this process a huge amount of wastewater is generated due to this mixing of these harmful gases and pollutants in the water streams. So when gas absorption reaction are required simultaneously with the particulate control, in such cases also we can use for these wet scrubbers. The advantages of these wet scrubbers are that these are capable of handling the flammable and explosive dust. They can also handle mist and process exhausts. They have relatively lower maintenance, and the design is relatively simpler and easy to install. And the particulate collection efficiency can be varied by choosing different types of methods for this wet scrubbing. And it also provides cooling for hot gases as discussed previously, and it also neutralizes your corrosive gases and dust. What are the disadvantages of these wet scrubbers? So first one is a large amount of water pollution problem is created due to this effluent liquid being generated. Also, the waste product is that is collected is wet, so the processing of that waste is like a bit complex or difficult as compared to that dry waste. Then we have high potential for corrosion problems due to moisture being present. Then it also requires protection against freezing, that it can't be used in conditions where we have very low temperatures. Then this method can't work in such situations. Then final exhaust gas requires reheating to avoid visible plume. Otherwise, if we have the exhaust air that is getting emitted from the outlet section, it will have moisture, so the plume will be visible. So that's why to avoid that, we should reheat the exhaust gas. Then collected particulate matter may be contaminated and not recyclable. Disposal of waste sludge may be very expensive. So these are the disadvantages of the wet scrubbers. Now coming back towards our question, which was this. What is the particle collection mechanism used in Venturi scrubbers? So the particulate collection mechanism, we have Brownian motion. Sorry, we are discussing Venturi scrubbers here, right? This is so the principal collection mechanism for the particulates in Venturi scrubber is your inertial impact. This one, inertial impaction. Oh, sorry, here, inertial impaction. Now, the next question. Which of the following statements is incorrect for the fabric filter? First is cleaning is required at regular intervals for efficient operation. Then improper filter media increases the collection efficiency. The normal velocity of airflow through the bags is zero point 0.4 to 1 meters per minute. The air to cloth ratio is the used for the fabric filter, which is the incorrect statement. Okay, so we'll just quickly discuss these fabric filters. So basically, in these fabric filters, the flue gas is passed through a tightly woven or felted fabric, and this causes the particulates to be collected on that fabric. Like it basically works out as a sieve, like the way we use our sieves in our homes to separate a certain thing material from the other. That is how we separate these particulates from the airstream in these fabric filters. So basically they are capable of efficiently collecting the particles which over the size range of 0.1 to 1000 micrometers. Like they have a wide size range of particles, like less than 1 microns, like it goes up to 0.1 microns, which is good. And the collection efficiency is also close to 99%, which is very high. So basically, the principle of these fabric filters is that as the particle adhere to the fabric, the particle efficiency increases because see this if this is your fabric, it will have certain pores in it, na, which will allow the gas to pass from one section to the other. So as the dust gets stuck on these, as the particles get stuck on these fabrics, what will happen is the pores will get like somehow there will be a layer of these particles that will be formed over the fabric, and the size of pores will be decreased. So that way like it will start trapping smaller size of particles. So that's why if, the collection efficiency is increasing, but also the pressure drop will also increase because it will be like it will also resist the flow of gas from this section to the outer section. So this is your total pressure drop in the fabric filter, which is your summation of the uh, pressure drop to the fabric and also the pressure drop to the caked or the adhered particles. And this is given by this equation. Here XR is thickness of the filter, XC is the thickness of the particle layer, KR and KC are the permeabilities of the filter and particle layer. Mu G is your gas viscosity, and V is the gas flow velocity through the fabric. So this is your pressure drop equation. Here, the air to cloth ratio is the main sizing parameter that is used for the fabric filters, and the gross air to cloth ratio basically it is defined as the actual gas flow rate at the maximum operating conditions divided by the total fabric area in the bag house. So this is how we can calculate the actual air to cloth ratio. And this is net air to cloth ratio. And this is used for multi-compartment fabric filters where one or more of the compartments is isolated from the gas flow due to cleaning or maintenance. And how to calculate the filter bag area? This A is pi dl. This is generally a cylindrical shaped filter. So this is your diameter of your cylinder. This is D, and this is your L. So the bag area is calculated as pi dl. Here, the important aspects like the particle collection mechanism, we have impaction, Brownian diffusion, electrostatic attraction as in the wet scrubbers also. And the efficiency during the pre-coat formation is low, but after the pre-coat or the cake is formed, the efficiency generally increases up to 99%. Because the pre-coat that is formed, it also acts as a filtering medium, and the accumulation of the dust increases the air resistance, and that is why the pressure drop is also starts increasing. So after a certain amount of time, we need to clean the filter media, or we need to clean the filter bags, because the pressure drop increases up to a certain level that it is like like approximately impossible for the gas to flow through this filter media. So that is why we need to remove this cake that is formed on the filter media. So they can be cleaned by either by wrapping or shaking or vibration or by reverse airflow. So by doing all these process, the filter cake will be loosened, and this can be fall down into the hopper, which is like certainly below this. Uh, like there's a collection hopper that is below this filter. The filter cake falls on that only. The normal velocities of airflow through the bags is zero point 0.4 to 1 meters per minute. And what are the factors that affect the collection efficiency of these fabric filters? So basically, there are two factors that affect the collection efficiency, or they may decrease the efficiency of the filters. First is your excessive filter ratios. That is a filter ratio, basically it is the ratio of the carrier gas volume to the gross filter area. So if per minute flow of the gas also. So if that is this ratio is very much higher, so what will happen is a large amount of carrier gas, will be passing from a very small filter area. So there's a high chance that the particles may not get properly trapped into that uh, cloth or the fabric of the filter. Next is also it lowers the particulate removal efficiency, and also it increased bag wear. So therefore, low filter ratios are recommended for high concentration of the particulates. If the particulate concentration is relatively lower, then we can have this filter ratio increased. Next is improper selection of the filter media. So basically, it also reduces the collection efficiency, because the properties like temperature resistance, resistance to chemical attack, abrasion, these should also be taken into consideration, because what kind of gas or what kind of particles we are dealing with is also very important to understand that what kind of filter media should we have chosen. because it's possible that we are using a cloth that like cotton cloth filter, and the particles are quite abrasive in nature, so the bag may tear apart, or the bag the that's why the filtration mechanism maybe get hindered. So the operating problem is first is cleaning. So in this process, the cleaning is required at regular intervals due to that, because of that cake formation thing. Next is rupture of the fabric. It occurs because of the shaking during cleaning, and is hard to locate, which decreases efficiency. The fabric may get ruptured at certain places because of the shaking of the filter. Next, we have temperature. So the temperature fluctuation may also cause various problems, because the higher for the higher temperatures, we should be having suitable filter media, because if the filter media is not resistant to higher temperatures, they may get like burnt, and that can also create a problem. Bleeding. So the penetration of fabric by fine particles. So the double layer material or thick woven fabric is used to counter the bleeding problems. What happens is the particles which are much finer, like less than zero point 0.1 microns, they may try to pass on from this fabric, or certain particles, maybe if the filter medium is not that thicker or is not proper, then might be possible that the particles tend to pass on from that fabric, and this causes the bleeding of those particles, and it will decrease the efficiency of the filter. Humidity. The moisture-free condition is required to maintain within the baghouse if the particulates are hygroscopic, because then the particles will tend to attract. If the particulates are hygroscopic, then and the moisture is present, the particles may tend to attract with the water droplets or the moisture, and then it may hinder the process of the filtration. Then we have chemical attack. So the possibility of chemical attack due to this corrosive chemical present in the particulates is also there. So the to select the filter media, we have certain like characteristics or the properties of the carrier gas that should be kept in mind. That what is the temperature of the carrier gas that we are going to pass on from the filter. Then what is the composition of that carrier gas. Then what will be the flow rate, and the size, and also the shape of the dust particles, and what will be its concentration. So these are the different types of filter medium that fabrics that can be used for the fabric filters, like cotton, wool, nylon, dacron, polypropylene, fiberglass, and we have maximum continuous operating temperatures, as these are the temperatures that these materials may resist, and like for example, cotton, it can resist temperatures up to 82 degrees centigrade, but its acid resistance is poor. Its alkali resistance is good, and flex abrasion resistance is very good. But its tensile strength is also way less, like it's 4920, and where fiberglass, it has a very high tensile strength, like 14,060. So it's very necessary to select a proper filter medium for a certain carrier gas. Knowing the properties of the carrier gas is very important. Now we have types of fabric filters. So first we have envelope type fabric filter. Here it is a form of a cloth envelope supported on a wire screen frame. The individual units range from zero point 0.6 to 1 meter wide and 3 to 5 centimeter thick. And the gas is introduced on the outside of each envelope, and passes through the fabric onto the flame of the unit and then out of the collector. So these are the screens, and these are the baffles that like the dusty air gets entered from this inlet, and then it passes from these chambers, and there are these screens. So these are the fabric filters that are placed, and the air, as soon as it passes from these screens and comes outwards, the particles get trapped in these screens. So that's how we get this clean air outlet, and then all this we have motor driven vibrators which certainly vibrates, and sorry, the dust gets settled down on this outlet and comes out. We can have this effluent or the gas, we can collect it from this outlet chamber. It's not suitable for very fine particulates. Then also we have multi-compartment type bag house. So if we need to continuously operate the filter, a multi-compartment type of filter bag is used, because if we are cleaning one filter, then others are being in operation. So it allows the individual units of the bag to be successively off stream during shaking, during the cleaning process, or sufficient cloth area must be provided to ensure that filtering capacity will not be reduced during the shaking periods, because when any one unit of the filter is off stream. So what are the applications of these fabric filters? They're basically used in metallurgical industries, foundries, then we have cement industries, then chalk and lime plants and ceramic industries, because the particles that are being generated from these industries are generally larger in size. We have flour mills also. What are the advantages? The advantages are that it has a very high collection efficiency, then then it operates over the wide range of gas flow rates, and the pressure drop is reasonably lower, and if it gets higher, then we can obviously remove that cake to get it lower down. And it has a good efficiency for smaller size of particles. Then we have the dry collection and disposal. The substrate that we collect, or the dust that is collected onto the hopper, it is dry, so we can easily dispose it off. So what are the disadvantages of these fabric filters? First is operating limits because of high temperature of carrier gas. It's high humidity and other parameters. Then we have high maintenance and fabric replacement cost. The size of the equipment is quite large, and it requires dry environment for its working. Then we have fire or explosion potential, and the problems in handling dust that may abrade or corrode or clog the cloth. So coming back towards the question, uh, there was a few statements regarding the fabric filter. So the cleaning is required at regular intervals for efficient operation. It is true. Next is improper filter media increases the collection efficiency. How is this possible? There should be proper filter media now that increases the collection efficiency. So it's not true. The normal velocity of airflow through the bags is 0.4 to 1 meter per minute. It's true. And the air to cloth ratio is the main sizing parameters. We have discussed this also. It is also true. So the answer will be B. Okay, so this is a question for the collection efficiency of the ESPs. And these are the terms, like where here eta is a fractional collection efficiency, omega is your drift velocity in meters per second. A is the available collection area in meter square. This is the collection area of the plates. And Q is the volumetric flow rates in a meter cube per second. So these ESPs. ESPs are generally used in many industries for the high efficiency collection of the particulate matter. Basically, here these plates are have certain charge in them, and this incoming gas, the particulates also have a certain charge. So for example, let's just say these plates are negatively charged, so we'll charge this gas stream as positive. So these particulates will get positively charged, and they get adhered to these plates, and then the clean gas comes out of this section. So it removes the particles which are less than 10 to 20 microns from a dust emission by using electrical energy to charge the particles either positively or negatively. This depends totally upon the charge on the plates. The charged particulate particles are attracted to the collected plates, carrying the opposite charge. And the speed at which the migration of the particles takes place is known as the migration or drift velocity. This is the formula to calculate the drift velocity, but in general, this is given in the question, what is the drift velocity of the particle? You don't have to find out the drift velocity. In some question, they may ask you to find out the value of this efficiency of the ESPs. For that, they'll be giving you the drift velocity, or this Kc. This is your Cunningham correction factor. So the formula for that is this. It is used for the particles which have a dia less than 5 microns. If the we are dealing with the particles of less than 5 microns dia, then we have to apply this correction factor to the drift velocity. The efficiency for the correct collection of particles from this ESP is given by the formula is eta is 1 minus e raised to the power minus omega a by q. This equation is known as Deutsch-Anderson equation. So if they want to twist this question now, so instead of finding out the efficiency of this ESP, they may give you the efficiency of the this ESP, and they may ask you to find out the area of the collection plates, this A value, or they may ask you to find out the drift velocity of the gas. So that's how the questions may be formed in the question paper. So this is your modified Deutsch-Anderson equation. Then we have your collection efficiency. So basically, there are very high collection efficiencies above the 1 micron dia due to the increasing effectiveness of contact charging for large particles. And question was this formula now. So this will be this efficiency of ESP is given by eta is 1 minus e raised to power minus a omega by q. This will be the formula. Collection efficiency. This one. Okay. So seventh question, the quantity of recirculation liquid used in the absorber divided by the outlet gas flow rate is called gas to liquid ratio, absorption efficiency, liquid to gas ratio, and adsorption efficiency. Okay, so these are the processes that are used to treat the gases that are present in the airstream. So the process is absorption. So basically, it refers to the transfer of a gaseous component from a gas phase to a liquid phase. But just the gases tend to get absorbed on the surface of a liquid, and the liquid surface area available for mass transfer and the time available for diffusion of the gaseous molecules into the liquid are important factors for affecting the performance of this absorption mechanism. And the gaseous contaminant being absorbed must be at least slightly soluble in the scrubbing liquid, which is termed as the absorbent. And at the saturation point, there's this equilibrium that is established between the mass transfer rate of the contaminant into the liquid and the mass transfer rate of the dissolved species back into the gas phase. So this is how absorption is done. The operating principle is first is absorber sizing. So we have liquid to gas ratios. The liquid to gas ratio is defined as the quantity of recirculation liquid used in the absorber divided by the outlet gas flow rate. The recirculation liquid that is known as the absorber, which is present in this chamber and which is divided by the outlet gas flow rate. This is your liquid to gas ratio, and it is important for two reasons. First is there must be sufficient liquid so that mass transfer equilibrium can be avoided, and there must be good gas liquid contact within the absorber. So this is your liquid to gas ratio. Now the next question. Biofiltration. So basically, it is a special type of absorption system which uses dash processes to control the gaseous contaminants. Like what kind of process are being used in biofiltration? Are these reversible or irreversible or equilibrium or both, reversible and irreversible. So let's discuss this biofiltration. So these treatment systems are termed either biological oxidation or biofilter systems, and the fundamental process involved in the collection of contaminants on the surface of a media that contains viable microorganisms. So this process involves the in this process the contaminants get collected onto the surface of a media, and that media have microorganisms present on its surface. So the contaminant is metabolized by the organisms, and carbon dioxide and water vapor are re-emitted. So accordingly, biofiltration can be classified as a special type of absorption, and this includes irreversible process because this includes the processing of that collected particles or the collected substances onto the filter media, and this processing can't be reversed because that material is degraded into the CO2s and water vapors which are emitted and during this operation. So these processes are clearly irreversible. So the operating principle is like this only. Uh, the conta After absorption into the thin water layers surrounding the packaging, the microorganism metabolize the dissolved organic compounds. Basically, it is used to treat the organic compounds which are present in the airstream. So the contaminated air is passed from the top of the chamber, and as the clean air comes out from the bottom, and during this process the particulates get trapped into these filter media, and it has some microorganisms present on it, so they react with the organic compounds, and then they form they release CO2 and water vapor from the degradation of those organic compounds. So the rate of destruction or consumption is usually measured in terms of the grams of pollutant per unit volume per hour. And this rate depends on the type of pollutant and the prevailing temperature that is there, because these bacteria tend to work better in at certainly warmer temperatures. So there are some terms that are involved. First is your empty bed resistance residence time, EBRT. It is a time it is the amount of time some unit of influent air would take to pass through the empty biofilter bed space when there are no particles trapped onto this bed space. Then how much time will this air to get will take to travel from the initial point to the outlet point? That is your EBRT, and it is always greater than the true residence time because of when the when we have the microorganisms and some particles are get also trapped onto the surface of those filter media, then the residence time will generally increase because the gases will take much larger time to travel from the inlet to the outlet chamber. So EBRT will always be larger than the TBRT. Now, this is the operating principle. So the volumetric mass loading VL is given by AF into C by VF. Here AF is your airflow rate, VF is volume of biofilter unit, and C is your concentration of CI is your concentration of influent, and C naught is your concentration of effluent. So the summary of this biofilter includes the general applicability is for this is generally used for the organic compounds, and the typical concentration is less than 1 ppm to approximately 1000 ppm. The gas temperature is generally 110 degree Fahrenheit, and it is applicable for control of multiple contaminants, and it's also used for the control of gas streams with particulate matter, but the pre-treatment often required for the removal of those particulate matters. Next, we have, I guess, answered this question. Yes, this. Which of the following primary forces is responsible for the particle collection in the cyclonic collectors? So we have electrostatic forces, and then Brownian diffusion, then we have centrifugal forces, then we have gravitational forces. So in cyclonic collectors, what type of primary forces? Okay, so these are dry cyclones, these are not wet cyclones. And sorry. So basically here dirty dirty air gets entered from this inlet wall, and after that it's like it enters this chamber tangentially. So due to this, what happens is that this turn to swirl around and come downwards. So as this moves, this gas swirls around in this cyclone now, the particles start to experience centrifugal forces on themselves. So due to that centrifugal forces, they get thrown away from the center, and they get stuck to the to the outside lining, or to the wall of the cyclonic chamber, and then they stuck onto the wall of the cyclonic chamber and tend to move downwards, and as they move downwards, they get collected onto this collection hopper, and this is the material outlet, and this clean gas, after coming towards downwards, then it certainly moves upwards from this clean gas outlet. So these are the this there's a vortex formation of this gas, and for which centrifugal forces tend to drive the suspended particles to the wall of the cyclone body. So the force that is responsible is centrifugal force for the particulate collection. So the collection of particulate matter generally depends on the centrifugal force that is generated inside the cyclone. So, and this centrifugal force in turn depends on mass of the particle, the inlet gas velocity with which the gas enters the cyclone, and the radius of the cyclone. Because the centrifugal force, the formula for this is mv square by r. So these are the three things for which on which this centrifugal force depends. And the greatest factor, the design factor, which has the greatest effect on the collection efficiency is the diameter of the cyclone. For a pressure drop, the smaller the diameter of the cyclone, the higher is the efficiency, because the centrifugal action increases with decreasing the radius of the cyclones. You can see this FC is inversely proportional to R. So as we reduce this R, this FC tends to increase. And as this F is increasing, more particles will get thrown out to the wall of the cyclone. So the efficiency will generally increase. And the minimum diameter of a particle that can be completely separated from the gas stream, this can be given by this formula. This 1T2, this will be 1 by 2. This is under root 1 by 2. The minimum size of particle, dp minimum, is 9 mu b upon pi v nt rho p minus rho raised to the power 1 by 2. And this cyclonic separator, it consists of a vertically placed cylinder that has an inverted cone attached to its base. This is the inverted cone that is there. And this cone also acts as your dust hopper. The particulate laden gas stream enters tangentially at the inlet point. This is a very important point. The gas doesn't enter straight onto the chamber. It enters tangentially into the cylinder, and the outlet pipe of the for the purifier gas is a central cylinder opening at the top. This is a cylinder that is opens at the top, which lets the clean gas to come out of the chamber. The dust particulates are collected at the bottom in a storage hopper. This is your storage hopper, which is there in the bottom. And the gas path generally follows a double vortex, because first this is your first vortex, and then it continues to move upwards. It's a double vortex. Firstly, the gas spirals downwards, and the outer periphery of the cylindrical portion continues to the conical portion and then reaches the bottom. Then it starts moving the upward in a narrower inner spiral. So that's why this is a double vortex formation, and this is concentric with the first one, and thus it leaves the outlet pipe. Due to this rapid spiraling movement of the gas, the deposits are projected towards the wall. The particulates, basically, they are projected towards the wall by centrifugal force, and then due to gravitational force, because due to their own self weight, they drop down from they slide from this wall towards the bottom of the body, which is your and they get collected onto this dust hopper. During cyclonic separation, the carrier gas rotational velocity exceeds several times the average inlet gas velocity, because of this rotational movement, the velocity increases. Okay, so the cyclonic efficiencies for particulates with dia of the order 10 microns, greater than efficiency is greater than 90%. And for particles with dia greater than 20 microns, the efficiency is about 95%. You can clearly see that as we increase the size of the particle, the efficiency gets increased in such conditions. And these can be operated at a temperature as high as 1000 degrees centigrade, and pressure 500 atm, and can also handle gas volumes that range from about 0.85 to 700 meter cubes per. Yes. Hello. Was anyone having any doubt? Hello. Am I audible?
Yes, ma'am.
So I thought someone was having any doubt. Okay, so I guess there's no one. So this is your a graph that shows the by which you can find this collection efficiency of these cyclones just by knowing the this particle size ratio d by dp. So here d is the average dia of the particle, and dp is the size of the smallest particle that can be removed in the cyclone. And by using this ratio, we can find this efficiency of the cyclonic separator. So you can clearly see, as this particle size ratio d by dp, as this value increases, the collection efficiency generally increases. So the collection efficiency increases if there is an increase in the dust particle size and the dust particle density. Also, as the inlet gas velocity increases, the collection efficiency increases. The inlet dust loading, as it increases, the collection efficiency also increases. And also the number of gas revolutions. You can understand this uh, um, by using the formulas of D and DPs. And the collection efficiency decreases if there is an increase in, first is gas viscosity or density. Then if the cyclone diameter, if it's increasing, then ultimately the value of this F is decreasing, and then the collection efficiency will also get decreased. This is the efficiency range of the cyclones for different size of the particles. And based on this efficiency, there are two classes of cyclones which are there, which first is conventional, and next we have high efficiency cyclones. These are the design parameters, how to design a cyclone. So These are the different sections for a cyclone. This is HC is your inlet gas, height of the inlet gas chamber. Then DE is your outlet chamber dia. DC is your dia of the cyclone. LC is your length of this chamber. ZC is your this conical chamber's length. So this is how to design a cyclone. Now, what are the operating problems which are there for a cyclonic separator? Basically, three important operating problems which are associated with the cyclones. First is erosion, second is corrosion, and third is material buildup. So, what is this erosion? So, very if the particles are very heavy, hard, or the sharp-edged particles are there, and if they are present in very high concentration, so they what they do is when they strike the wall of the cyclone, they scrape it against the wall of the cyclone, and thus they can erode the metallic surfaces unless the less suitable materials are used. If the material is not of that good quality, then these particles may tend to erode the material of that cyclone. Next, we have corrosion, that if the cyclone is operating below the condensation point, basically if they are when the reactive gases present in the effluent stream, and so the problem of corrosion may occur. So the best solution to any corrosion problem in a cyclone is to keep the product above its dew point. So for that, no moisture will be there, and thus we can avoid this corrosion problem. And if the gas and dust are corrosive at low temperatures, then perhaps the only alternative is to use a stainless alloy, so that corrosion can be avoided. Then we have material buildup. So buildup of dust cake on the cyclonic walls, especially around the vortex finders, at the ends of any internal veins and opposites, the entry can become a severe problem. It occurs most frequently with the hygroscopic dust because this can get attached to the moisture, and then it can get collected onto the surface of the hopper or to the inlet chamber. In case the dust buildups on the wall of the cyclonic cone, a simple solution is to pound on the cone with a sledgehammer, or the other solution is to hang chains inside. This works, but it certainly reduces the efficiency because it tends to eff- hinder the movement of the gas inside the chamber, and thus it creates a resistance, and the velocity gets reduced due to this hanging the chains inside the chamber. A better solution is to flange the section to provide a rim between the dust collection hopper and the cyclone body, and which can be removed periodically and scraped to remove that buildup of material. Now, what are the applications of these cyclonic separators? So, first is control of gas-borne particulates in industrial operations such as cement manufacture, feed and grain processing, food and beverage processing, mineral processing, paper and textile industries, and woodworking industries. So, these are the applications. And this can be also be used to separate the dust in disintegration operations such as rock crushing or handling and sand conditioning in industries. This is also used in the recovery of catalyst dust in the petroleum industry and the reduction of fly ash emissions. And application on the basis of their application, there are two types of cyclones. First is multiple, and second is cyclones in series. Okay, so coming towards the last question, which device is fitted in vehicles to control the air pollution from the tailpipe emissions? First is electrostatic precipitator, second is catalytic converter, third is bag filter, and then we have cyclone separator.
Catalytic converter.
Yes, that will be catalytic converter. Okay, so that's all for the questions for week 9 assignment. If you guys are having any doubts, you may ask them.
Ma'am, I have a doubt, ma'am.
Yes.
Ma'am, in lecture 41, slide 8, there is one concept called rain out, ma'am. I can't understand that.
Okay, let me take that lecture 41, slide 8. Okay. Just wait. Let me share the screen now. Okay. So, is this natural self-cleansing property? Is this slide visible?
Yes, ma'am. I can understand rain out, ma'am.
Okay. So basically, rain out is a natural self-cleansing mechanism to remove the particulates from the air. So what happens is now the when the submicron particles, the smaller size of particles present and on the upper atmosphere, they start acting as a condensation nuclei. What is condensation nuclei? Basically, these particles tend to attract the water droplets, and it what happens is these around these smaller particles, water gets attracted to them, and then clouds are formed. So and when these clouds are formed, then eventually what happens is they like fall out as raindrops. So this is a process of rain out. So basically these ultrafine particles which are present in the atmosphere, in the upper levels of the atmosphere, they tend to help us in the increased amount of rainfall and also in fog formation in the urban areas, because they serve as sites to attract the water vapor in the atmosphere. This condensation nuclei thing, because they attract the water molecules onto their surfaces, and then they aid in formation of the clouds. And after that, when rainfall happens, they fall down onto the ground with these water droplets, and they get removed from the atmosphere. So that is how these particles get removed from the air or the atmosphere.
And what is the
Now,
difference between rain and rain out, ma'am?
rain out basically is a process to remove these particulate matter. Rainout is this process of the precipitation above the cloud level. Basically, this is the process of attracting those water molecules onto the surface of those submicron particles. This is rainout. And the rain is basically that precipitation, that falling of water droplets from the clouds towards the ground. That is rain.
Thank you, ma'am.
Okay. Any other question? Oh, excuse me. Anyone else? Okay, so I guess if you guys don't have any questions, then we may end the class for today.
Thank you, ma'am.
Okay. Okay, so since you guys don't have any other questions, we'll end this session here. See you guys the next week, and we'll have week 10 assignment questions in that week only. Okay, see you. Thank you.